Hey everyone, and welcome back to the channel. We talk a lot about how AI is getting incredibly good at complex tasks, but one area that really pushes the limits is advanced mathematics. It's not just about getting the right answer, but how the AI gets there. Can it reason deeply like a human mathematician? And maybe more importantly for practical use, can it do it efficiently without burning through a mountain of computational resources? That balance between accuracy and efficiency is a massive challenge, especially in tough competitions like the AI Mathematical Olympiad or AIMO. Today, we're doing a deep dive into a really clever solution that tackled exactly this problem. The ninth place solution for the AIMO Progress Prize 2, called Fast-Math-R1-14B, will break down their approach, look at the code, and figure out the secret sauce behind how they made their AI both smart and fast at math. Let's get into it. Right, so this is the solution we're analyzing today, Fast-Math-R1-14B, developed by Hiroshi Yoshihara, Yuichi Inao, and Taiki Yamaguchi. It's their approach for the second AIMO Progress Prize competition. Just a quick refresher on the competition itself. AIMO Progress Prize 2 is about really challenging math problems. Think National Olympiad level stuff, designed specifically to be tough for current AI. We're talking algebra, combinatorics, geometry, and number theory. The goal? Simply predict the final integer answer between 0 and 999. Evaluation was based purely on accuracy. How many did the AI get exactly right? Now, to really appreciate the difficulty, let's look at an example problem they might face. Count the number of four-digit numbers A, B, C, D, where the first three digits, A, B, and C, are three consecutive integers in some order, and the whole number A, B, C, D is divisible by 3. You can see here the kind of reasoning needed. You have to think about permutations, the fact that a can't be 0, properties of consecutive integers, and divisibility rules. It involves multiple steps and careful case analysis. The answer is 184. Getting an AI to reliably follow this kind of logic is tough. And this example perfectly highlights the dual challenge we talked about. First, you need that deep mathematical reasoning. Second, generating a detailed, step-by-step proof like the one shown uses a lot of tokens, which means more computation time and cost. The big question this team tackled was, can we get that high accuracy and cut down on the reasoning cost? Their answer was Fast-Math-R1-14B, the core strategy. Take a strong base model and fine-tune it in 2 specific stages. Stage 1 focused on boosting its accuracy on these hard math problems. Stage 2 then aimed specifically at making the reasoning process more token efficient. The result? A model that's significantly faster, using up to 60% fewer output tokens, while staying highly accurate. Here's a visual of that process. You start with the base model, put it through Stage 1 SFT training focusing on accuracy, then through Stage 2 GRPO training focusing on efficiency, ending up with the final fast math model. Pretty logical flow. So, what was the base model? They chose DeepSeek R1 Distill QN14B. This is a capable 14 billion parameter model, built on the QN architecture, distilled from DeepSeek R1, and probably already pretty decent at reasoning, thanks to distillation and alignment. Okay, Stage 1 is Supervised Fine-Tuning, or SFT. The goal here was purely about improving mathematical ability. They didn't just use any math data. They curated a dataset specifically targeting difficult problems. They pulled from sources like OpenR1 Math, filtered for problems that needed long reasoning or where models often failed, and combined it with other hard datasets like OpenR1 Hard and LightR1 SFT data. They deduplicated, picked the shortest correct reasoning trace if multiple existed, and ended up with about 7,900 challenging examples. How did they train? They did full parameter SFT using the SFT trainer from Hugging Face's TRL library. To handle a 14B model with full parameters, they used DeepSpeed 03 via the Accelerate library, essential for fitting this into memory on their 8H200 GPUs. They ran this for 20 epochs. Now, before we dive into Stage 2, we need to understand the key algorithm they used. GRPO. It stands for Group Relative Policy Optimization, introduced in the fantastic DeepSeek Math paper. So, what is it? Think of it like other AI training methods based on feedback, like DPO or PPO, but with a twist. Instead of just comparing two different answers or giving a single score to one answer, GRPO looks at a whole group of answers the AI generates for the same prompt. Here's the basic idea. First, the AI generates, let's say, 8 different responses to one math problem. Then, you figure out which one of those 8 is the best. Maybe it's the one that got the right final answer, or use the most efficient reasoning path based on those reward functions we'll discuss. The magic of GRPO is in the next step. It updates the AI by specifically trying to make the best response more likely relative to all the other responses it generated in that same group. It's learning from the relative differences within its own set of attempts for that single prompt. Why do this? Comparing within a group like this can give a more stable and perhaps richer learning signal than just looking at pairs or absolute scores. It forces the model to really distinguish why the best response was better than its own other tries. All right, stage 2, applying GRPO. The goal now shifts to efficiency. They took the model from stage 1, which was already good at math, and trained it further using GRPO. The dataset used problems from light R1 SFT data. The crucial part here was the design of the reward functions. They used that faster GRPO trainer implementation with DeepSpeed 02 managed via Accelerate. Only one epoch here, but it involved generating 8 completions per prompt for the reward calculation. This slide is key. The innovation really lies in these custom reward functions defined in fine-tuned GRPO reward script. They used 3 main ones. One format reward. This one is key. It gives a reward only if the final boxed answer appears before the special think tag in the output. It enables a massive efficiency trick. More on this in the next slide. 2. Cosine reward. This provides a smoother signal than just right or wrong. Correct answers get more reward if they're shorter, and incorrect answers get less penalty if they're longer using a cosine curve. It gently nudges the model towards conciseness when it's right. 3. Length reward. This one is more direct. It simply penalizes longer reasoning paths, explicitly discouraging the model from overthinking or adding unnecessary steps. These rewards work together beautifully. The format reward sets up the mechanism for speedup, while the cosine and length rewards train the model's general preference for being efficient. So, how did they actually achieve that 60% speedup? It wasn't magic. It was clever engineering based on the GRPO training. First, that format reward trained the model to put its answer down before it finished thinking, marked by a think tag. Second, and this is critical, look at their inference code snippet. They used VLLM, a fast inference engine, and set the stop parameter to think. This means as soon as the model generates that think tag, VLLM immediately stops generating tokens. It doesn't let the model ramble on after it has already found the answer. This directly cuts down the number of output tokens. Third, the cosine and length rewards helped too, by generally making the reasoning before the think tag more concise on average. And finally, using VLLM itself gives some speed benefits. But the main trick here is that GRPO training enables early stopping. It's not just faster tokens, it's fewer tokens. Let's peek under the hood at the tech stack. Standard stuff like PyTorch and transformers, of course. Hugging Face TRL was key for both the SFT and the GRPO training loop. Accelerate and DeepSpeed were essential for handling the distributed training and fitting the 14B model efficiently. For inference, VLLM was crucial. Now, bridging the gap between a model being trained with DeepSpeed and running inference with VLLM requires some coordination. That's where their custom VLLM sharding manager comes in. Think of it as a traffic controller. When it's time for inference, which happened during the GRPO reward calculation phase, this manager copies the latest weights from the training model over to VLLM. Then, to save precious GPU memory, it temporarily kicks the big DeepSpeed model and its optimizer off the GPU. After VLLM finishes generating, the manager loads the training state back onto the GPU. It's a smart way to juggle resources. Okay, the results. In these charts plot, y-axis is pass at 1 accuracy, higher is better. X-axis is the average number of output tokens, lower is better. So that means you want to be in the top left corner. See the green line? That's Fast-Math-R1-14B compared to the blue DeepSeek base and orange light R1. The green line is consistently further left, showing it uses fewer tokens for similar or better accuracy. The table gives us the key numbers. Look at the highest token budget, 16,384. Fast Math matches the accuracy of the best competitor light R1, but uses about 2,000 fewer tokens on average. That's over 20% less. Now, look at the lower budgets, like 8192 tokens. Here, Fast Math is actually more accurate than both competitors, while still using significantly fewer tokens. This really shows the power of that efficiency-focused GRPO stage. It delivers on the Fast Math name. They also built an interesting side component, a token scheduler. This is a separate, smaller BERT model trained to predict how many tokens the main Fast Math model would likely need to solve a given problem. You could potentially use this to estimate compute cost or prioritize easier problems first. It wasn't core to their competition rank, but shows some interesting thinking about meta strategies. The code and data for this are also released. One last crucial detail for math problems: evaluating the answer. It's not always straightforward. First, extracting the answer. It pulls the potential answer from the model's output, often looking for that boxed pattern. Then, remove the irrelevant tokens and clean up the string. Finally, check the math. It compares the cleaned prediction to the ground truth. This isn't just simple string matching. It uses numerical comparisons with tolerance. More importantly, symbolic comparison like SymPy library is used to see if two expressions are mathematically equivalent even if they look different. This robust evaluation is vital. So, what are the big takeaways here? This was a fantastic demonstration of a two-stage fine-tuning process. SFT first to build core capability, then GRPO, a form of RL to optimize for a specific behavior, in this case, efficiency. The custom GRPO rewards were the secret sauce, especially that format reward enabling early stopping. That's a technique others could definitely adapt. They achieved that sought-after balance: top-tier accuracy combined with significantly reduced computational cost. And huge kudos to the team for making their model, datasets, and code open source, a massive contribution back to the community. If you want to dig deeper yourself, everything is available online. The model is on Hugging Face and Kaggle models, the datasets are on Hugging Face, and the complete code is on GitHub. They also have a detailed write-up on the Kaggle discussion forums. I'll drop links to these in the description below. Alright, that's our breakdown of the Fast-Math-R1-14B solution. Pretty cool how they combined targeted training data, reinforcement learning with custom rewards, and clever inference tricks to make a math AI that's both accurate and efficient. It really highlights how fine-tuning strategies are evolving beyond just maximizing accuracy. What do you think of this approach? Let me know your thoughts down in the comments. If you found this video insightful, please consider subscribing for more content on AI competitions, machine learning techniques, and practical data science. Thanks so much for watching, stay curious, and I'll see you in the next video.